My screen's here.
Yes. That works.
Hey, all right. We figured it out.
All right. I'm a YouTuber, so I'll do video.
All right, hi. So we are the Curious Marc Restoration Group. Marc Verdiell, Mike Stewart, Ken Shiriff, Eric Schlepfer. And we are talking about this Apollo DSKY that we restored just recently. So the DSKY, which is short for Display and Keyboard, is the astronaut interface to the Apollo guidance computer, which is the gold box on the left there. The Apollo guidance computer was a small computer for its day. It weighs 50 pounds. It has 4 kilobytes of RAM, 72 kilobytes of program memory, and all of the astronaut interfacing with this computer was done through this box, the display and keyboard. The display and keyboard, the DSKY, was mounted on the main control panel right in front of the commander in the command module. Here's another shot of that in one of the simulators of a DSKY lit up. The command module actually had 2 DSKYs. One of them was also located down in the lower equipment bay right next to the optics. The optics composed of a telescope and a sextant that they were able to mark stars with to determine what their attitude in space was and figure out where they were. So they've located a DSKY right next to that because that's heavily involved in guidance operations. So most of the star marking was done through this DSKY. And then there was also a DSKY, almost exactly the same except for the alarm lights, in the lunar module. That was positioned right between the commander and the lunar module pilot. It's Neil and Buzz in this picture. So this specific DSKY was just sold by RR Auction recently for quite a sum. There are a lot of DSKYs in museums and a lot of collectors that have DSKYs, but it's been very hard to get anybody to agree to let us turn one on. People are usually pretty protective of this hardware. But luckily for us, one of our collector friends just recently picked this up in the auction after it was sold a couple times. So that's this unit that we have sitting here. From its serial number 39, we know that this specific unit was used in the simulators at MIT. The MIT Instrumentation Lab, now known as Draper, was the group that designed basically the entire guidance system for the both spacecraft, including this DSKY. This is a shot of the simulator, the command module simulator at MIT. It's hard to judge from this picture, but the DSKY shown here might be this one. We're not entirely sure, but the keys kind of line up with what this one looks like. So as you might have seen from the auction slide, our DSKY was very slightly broken. If you look really closely, you can see the problem, which is a sticky 0 key. And also the screen, I guess. So the screen is really interesting. It's an electroluminescent display. It's low power, but it's powered by high voltage. It takes 250 volts at 800 hertz. It's flat, it's cold to the touch. The screen is basically completely insensitive to vibration. And it has a very limited lifetime. After 2,000 hours, it's lost 60% of its brightness. So when they were doing ground testing of all the vehicles, they made sure to have the brightness on this display turned almost all the way down so they could barely see it, just to preserve the life for the mission as much as they possibly could. The construction is really interesting. You can kind of barely see it through the crack in the glass there, but it's composed of a glass panel onto which electroluminescent phosphors have been deposited, and then there's these little metal pins that stick out and contact the phosphors to light up the panel. This is a block diagram of what all is inside the DSKY. It has a high voltage power supply, takes in 28 volts and 14 volts DC, and then an 800 hertz clock from the Apollo guidance computer. There is 132 relays in this box, which is complicated to address. So they have a column and row scheme that lets you address groups of 11 relays at a time. There are another bank of relays used for caution and status lights. The keyboard, which is a diode matrix running at 28 volts. And then there's the electroluminescent display itself. So cracking open the DSKY, this is what it looks like when you remove the back panel. There are 7 modules in it. There's the power supply module, the little one in the back. And then there are 6 modules called indicator driver modules, or IDMs. Each of these 6 IDMs is completely identical. Each one contains 22 relays and a section of the logic and circuitry required to drive them. And the relay matrix is really complicated. There's several sheets of this showing how all the relays are interconnected all through the backplane. So taking it apart further, just to make sure that, before we try to turn it on, that it's all complete and nothing inside is damaged. This is a picture of us separating the 2 halves. And this unit turns out to be in really good shape. Everything is there. The inside is mostly potted, so we can't get to a lot of the wires, but that also means that probably nothing down there has been damaged over time. So then we have to deal with that broken screen. So to access the screen, you have to remove this front cover. And then the screen just unscrews with these 6 screws. It's actually very easily serviceable. The back of the screen has a very large pin array, basically one pin for each segment, using Malco mini wasps, which were a series of connectors that seems to have only been used for the Apollo guidance system and almost nothing else. It's very hard to get your hands on contacts that will mate with these, but luckily we don't have to deal with that. The other thing that we have to do while we have the front off is deal with that sticky 0 key. So this picture was taken with the 0 key removed. It kind of shows the construction of these keys. They were completely custom built. You can see the silver micro switch on the back there. It's a hermetic micro switch that sells for like $2,000 a switch or something. And then that's mounted onto this, this little housing that is airtight because they wanted to pressurize this and keep any fire situations from damaging the command module. And then this is the key itself. It has a double spring arrangement. So there is the spring, the coil spring, that actually pushes the key back out. And then there is a leaf spring that comes down and contacts the micro switch and causes the micro switch to close. So with the broken screen out, we plugged it into our DSKY display tester, which is something that everybody has. And we're just curious if this would light up because it's pretty heavily damaged. And sure enough, it does. It tries its best. Not all of the segments come on, and there's a crack that goes sort of diagonally down, and nothing below that crack turns on. But it works remarkably well for something that is as damaged as it is. But luckily, our friend had previously bought a flight spare display that only had 10 hours of operation at the time that they had last tested it. So he also had a prototype display from early in the program. So we had our choice of displays that we could plug into the unit. And we decided to use the newest one, the one that only had 10 hours of operation. So this is very close to a flight unit. It's basically identical to a screen that would have flown. So to drive this thing, we 5 years ago restored a real Apollo guidance computer, but the owner has since sold it off. So we're not able to hook this up to a real Apollo guidance computer at the moment. So instead, I designed a little board that has an FPGA. That FPGA is running a gate-exact implementation of the Apollo guidance computer, and also an implementation of the test equipment that they use to test the AGC. And then the board implements all of the basically level shifting circuitry necessary to convert the keyboard logic levels down to something safe for the FPGA and to be able to drive enough voltage to make the relays flip. The other problem is that there is a circular connector on the back of the DSKY made by Deutsch. It's a high-density Deutsch connector. And those also seem to have only really been used for the Apollo program. They never made it to a mil spec. And TE connectivity will still make them for you if you're willing to pay $40,000, which I don't want to do. So the way that we are hooked up to it right now is I SLA printed a compatible insert and pressed contacts into it, and then connected that to a ribbon cable, or not a ribbon cable, sorry, a DD50 cable. So with everything wired up, it should work, and we're going to demonstrate it for you here in just a second. When you see things on the DSKY, this is how you read it, basically. There is a bank of alarm and status lights on the left, keyboards down at the bottom. The electroluminescent display on the right shows you the current program that you're in, the verb and noun, which is the way that you interact with the thing, and then up to 3 lines of data. Those 3 lines of data give you absolutely no context for anything that they're displaying. It doesn't say anything about what the numbers represent. There's no units. And there is an implied decimal point on many displays, but there are no dots on this display. So when you put up a certain noun, you need to memorize where the decimal points are for that specific display. So let's get wired up to actually show this. Hello? Hello? All right. Cool. Okay. So I have my FPGA plugged in. I'm going to really quickly load it with the Apollo 11 lunar module software. I don't think I can because the HDMI cable is over there. And it doesn't reach this far. I will get this on in just a second. Oh, okay. Yeah, that would be great. How many connectors, or how many contacts, how many pins are there in this cable? So, thank you. It is an 85-pin connector on the back of the DSKY here, and I am connected to 44 of them. Because of the modular design of the DSKY, there were several spare relays, and since they had these relays that the computer could control, that they had to fly, they decided to use those for other purposes. So one of the relays in the lunar module controls the landing radar position. One of them in the command module is a backup command to the Saturn V to do translunar injection. Just random things. And so all the other pins on the back of this are not used for displays in the DSKY, but they're used for those ancillary purposes. All right, so this is the interface to my FPGA. It's like a blinking lights panel, very similar to what they had for development back then. So let me get the DSKY on. So I'm going to turn on 28 volts first, and then 14 volts and 5 volts. All right, there we go. So I'm just going to run through some things here. I do want to point out all of the buttons do work. So if I do a verb 35, enter, there's the lamp test. It turns on all the lights. I can also inject commands or key presses through this interface, which I'm going to do now so I don't have to do it upside down and in front of the display. So I'll do another lamp test really quick. Verb 16 is display 3 decimal numbers once a second. Noun 65 is our current elapsed mission time. So this is showing hours, minutes, and centiseconds. Remember the implied decimal point there. Let's see what else is interesting. Verb 34 stops the running display. Verb 91 is a means of checking the validity of the software. This adds up all the words in the bank and shows you the sum, so you can verify that, in fact, there are no errors in your software. You can just proceed through each bank. So we're looking at bank 4 now, bank 5. But the really interesting thing is we can go through the initial landing sequence for Apollo 11. We have a very highly detailed simulator of the Apollo spacecraft that runs emulators of the Apollo guidance computer. And we extracted the RAM state from one of those flights. And I have just now injected that state into my FPGA. So if I do a verb 16, noun 65, to look at our mission time, we're now 102 hours, 34 minutes, and 15 seconds into flight. This is right before the landing burn starts. Powered descent initiation, PDI is what that's called. So if I do a verb 37, enter, 63, enter, this gets us into powered descent initiation. So what the computer is doing right now is it is looking at our orbit and our landing site and trying to calculate the burn that is necessary to get us there. And the fact that we have made it to this screen means that it was able to complete that computation. It'll be a 9-minute and 50-second long burn. That burn will be starting in 1 minute and 45 seconds. And it is 0.7 nautical miles cross range to our landing site, I believe.
So you guys have about 11 minutes left. Just letting everybody else know, if you're here for the Atari talk, it's going to start a little bit late, but we'll be on following this.
All right, so only have a little bit left here. So this screen is our current attitude. This was the screen that we would use to maneuver the spacecraft prior to the burn to get it facing the right way. And then these screens are the computer yelling at me and telling me my switches are in the wrong position because I'm not connected to a real spacecraft, and so I don't have switches to be in the right position. But I can just tell it to ignore that and move along. And what it's doing right now is propagating our position from the last point that it had saved in the orbit to our current position so that it can then start incorporating readings from the accelerometers into our state vector. I just got a program alarm, and I think that's because I took too long, and it pushed back our ignition time a little bit. That is fine for our purposes here. So it pushed back our burn by just a little bit. It's now going to start in 40 seconds. I'll reset that program alarm. The screen is going to blank now at T-minus 35 seconds. That tells us that average G, which is the software that actually incorporates the accelerometers into our state vector, is now running. And if you see, the top row now is changing where it wasn't before. So this is updating our velocity in real time. So we are now 10 seconds away from our burn. At minus 5 seconds, it's going to start flashing verb 99 at me. And if I press proceed now, that accepts it, and it begins doing the burn. This is the point at which we have to stop because we're not hooked up to a real spacecraft. There's a piece of software called the Delta V monitor running that is looking for a change in velocity. And it's not seeing my velocity change from the engine being on, so it's flashing a verb 97 at me telling me that my engine has failed, which is a sad day. But yeah, so Zerdisky, everything works. Verb 35, do another lamp test. Oh yeah, yeah. I'll hold the microphone up to the disky so you can hear the relays clicking a little bit, hopefully. Does that work? Does that work? Yeah. Okay. Yeah. Let me do a lamp test. And I'll clear the screen. Put up the clock. Now 65. There we go. Yeah, we weren't expecting the relays to be so audible. We had no idea. We thought that since it's in a pressurized enclosed box, they might not be. But it makes a really, really satisfying sound when it changes the display. So I think, did you guys have anything to add? Or Mark? Cool. Yeah, open for questions then.
If you have questions, let me know and I'll come to you. We have about 8 minutes.
Are you guys able to make new electroluminescent displays, or is it like when that new old stock one dies, it's gone forever?
So Ben Krasno of Applied Science made a really good electroluminescent display. He could probably make something that would work. He did a really, really good job, but it really doesn't do the original justice. The contrast is not as good. So it would be very hard, I think, to make a decent replica of it. But you can make an EL panel that will work for sure. If you're Ben, probably. It involves a lot of chemicals.
You mentioned that it was low power. How much, like how many watts does it actually draw with all the power supplies?
That's a good question. My gut reaction is 11. The power supplies aren't really registering that much, honestly. The main power is these lamps. All of these lamps are like 250 milliamps apiece, which is why they're dimming when I turn all of them on.
Yeah, the whole thing is very low power. The electroluminescent doesn't consume anything, and then the relays are latching. So they solve kind of 3 problems. They solve the switching of high voltage. They solve the problem of memory, but they also solve the problem of power consumption, because the only time you have to power them is when you switch them from one state to the other. So that's why you are not registering any current on the power supplies.
Yeah, 28 volts is pulling around 3 to 5 watts right now.
But that's for the lamps.
Yeah, exactly.
So the EL is extraordinary for this low power consumption.
Other questions?
Where does the power come from on the spacecraft? Is it just batteries, or does it have a thermoelectric or a radioactive generator?
So the spacecraft has fuel cells. It converts hydrogen and oxygen into power and drinking water. That charges up and is backed up by batteries. And then there's.
So is the lunar module just batteries?
The lunar module is just batteries, yes.
Other questions?
Trying to understand the use of the verb noun means by which to control the computer. What was the MIT engineer's decision to go with that instead of like program number or something like that? Why do they choose verb noun as a mean to organize the various programs?
My understanding is that there was not a lot of thought put into that. It was something that somebody came up for a demo, and it just kind of stuck. But when you're dealing with just like a completely numeric interface, it's kind of a natural way to allow you to, at least in number form, do something to something. It makes a lot of sense if you can make that mapping as interchangeable as possible.
So basically, the verb says what you want to do, and the noun says what you want to do it to. So the verb could be anything from look at contents of memory to start an engine, and then the noun would be, what thing you want to look at in memory or what star you're finding the position of. So it's a pretty flexible, sort of user interface. But it takes a lot of memorization and data to be able to know what are all the verbs by number and what are all the nouns by number.
In the spacecraft, they had these things called cue cards mounted with Velcro right next to the DSKY that was a list of all the verbs and nouns, so they could just look over and, make sure that they're thinking of the correct number.
Other questions?
How long did it take you to make the FPGA?
The FPGA took me probably 6 months of work in my free time, and then a little bit of work time during one of those times where my team was told to stop working for a little bit because of acquisition nonsense. So I did get paid full-time to work on the FPGA briefly, which was great. But it was probably about 6 months of work between drawing up the schematics in KiCad, writing the Verilog generator from that, making that Verilog compatible with FPGAs. It started out as unsynthesizable Verilog. I had to make some tweaks to get it into an FPGA. And then testing it and finding the bugs. That was a whole saga of, at the time I did this, we didn't have the self-test software for this computer. So we didn't have a good way to verify that it's correct. We've since found that, luckily. But yeah, it was quite a process to get that FPGA working.
We have time for just one more. All right, last question.
Your projects are always or often an amazing mix of different hardware and software things. I'm just wondering what all your backgrounds are.
So my background is software. I got into electronics as a hobby because having software as a job made me not want to do software at home. I like to tell people I do flight computers at home and flight computers at work. I do flight software for spacecraft as my job, and then I do the same thing as my hobby, just 50 years removed.
My background is operating systems, so this really doesn't have a whole lot to do with my background, but I do a lot of hardware stuff and reverse engineering just for fun.
And my background is electrical engineering, but there's also some software in there too, mainly embedded type stuff.
And my background is fiber optics communications on the component side of things, which is a mix of optics, mechanics, RF electronics.
All right, well, thank you guys. This is a great presentation. Glad we could fit it in. Everyone give him a big hand. All right, any last words before we go?
I don't think so. Thank you for slotting us in.
You're welcome. All right, thank you. So.